With the following two exercises, we want to practice what we learned so far about structure files and how to optimize refinement strategies. And in the second example, about creating instrument configuration files. And the first exercise is based on our example file number 1, the mixture of calcite and hydroxyapatite. And I will show now from the start to the end how I optimize this refinement. So first we start by loading the scan file. I will choose the modern file format, the BRML file. And we have already identified the phases before by double-clicking on the strongest peak. For example, on this one, we find apatite O or apatite OH, hydroxyapatite. And by double-clicking this one, we find calcite as the best match. So to create a refinement project with calcite and hydroxyapatite, I go to the Add Remove Phases dialog. I have to select my instrument configuration, which is the RMS D8 ADS instrument. Not the one with glass in the name, that's for the capillary configuration, but the one without glass. And then I use the filter function to find my phases, first apatite. Then I will pick apatite OH and calcite. There are many calcite structures in the different repositories. I will pick the one from the minerals subfolder. Now it has created the refinement control file, the SAF file, and copied these two structure files to my working directory, and I can immediately start the refinement and see what we get. As discussed earlier today, my first check is if there are any additional peaks that do not belong to calcite and hydroxyapatite. In that case, I would still have to complete my phase identification. So I zoom in a little bit and I see that all the peaks either belong to calcite in green or apatite in blue. So my phase quantification was successful and complete. Now I can continue and optimize this refinement. And the most obvious misfit I can recognize in the difference curve is the strong calcite peak here. And if I zoom in, I see that it's the peak width and also a little bit the intensity that doesn't fit correctly. So obviously something with the peak broadening is not correct. And I will go to my calcite structure file and just check how this peak broadening was refined. The broadening parameters are the B1 parameter for crystallite size related peak broadening and the K2 parameter for microstrain related peak broadening. And I can see that the B1 parameter was refined isotropically, but K2 was not refined. So my first guess would be that there might be some microstrain, and I want to refine the K2 parameter to account for this type of peak broadening. So I set this by right-clicking on the K2 parameter. I set it to refine isotropically. And then I will repeat the refinement and see if the fit improves. Before I start the refinement, I will check my current chi-square value down here in the refined parameters. It's 2.41. And if this improves significantly with the new refinement strategy with refining K2, it was probably a wise decision to refine K2. So now we start the refinement and see what we get. Now the chi-square parameter is 1.7, which is a lot lower than 2.4. And we can also see at the difference curve that the misfit is now significantly improved. The misfit is less than it was before, the fit is improved. But if we zoom in, we still see that the width of the peak is not exactly what we measured. And now in the difference curve, we see that it's a symmetric pattern. So at the in the flanks of the peak, we have over-refined a little bit, but the tip of the peak is under-refined a bit. And now I recognize this kind of difference pattern, and I want to show you a trick we have not discussed yet. So what we see here is a sign of a bimodal crystallite size distribution. So obviously the peak is fairly wide, especially in comparison to the apatite peaks here, where we can resolve K alpha 1 and K alpha 2. We cannot resolve them in the calcite peaks, so we already have quite a bit of peak broadening. But there might be a coarser fraction that is not quite as broad as this, and this coarser fraction would have slightly sharper peaks, and they would overlap exactly the white peaks we see here. So in a bimodal crystallite size distribution, we have a fine fraction and a coarse fraction, and we need to refine the peak width separately for these two fractions. And the way we do this in Profex is fairly simple. In the calcite structure file, we need to add some predefined code. So I will make some space here, add some empty lines after the profile refinement line here. And then I go to this button here, the text block button. And this is just a collection of some predefined code I prepared in Profex, some code I use very often, so I don't have to type it manually each time I want to use it. And there is one block for bimodal crystallite size. And it inserts these lines. And I don't want to go into too much detail, but basically we split this phase into two subphases. So we can now address them with Gewicht index 1 and Gewicht index 2. And also the peak broadening, B1, we can address with B1 index 1 and B1 index 2. And this allows me to refine two different peak broadening parameters B1 for the subphases within the calcite structure file. And now we can repeat the refinement again. And we want again to take note of the chi-square parameter and see if it improves below 1.7. And we see a slight improvement. It went to 1.64, which is not much better than 1.7, but it is going in the right direction. So now if we look at the refinement, we refine microstrain and we refine bimodal crystallite size distribution and a moderate texture model. Now before we continue and try to refine the substitutions on the calcium sites, let's just try to max out the refinement of the profile. So at the moment we are refining in the calcite structure the peak broadening isotropically for the crystallite size contribution and also isotropically for the microstrain contribution. And we do not refine the K1 parameter, which describes the particle size distribution or crystallite size distribution. And just to max it out, we can try to refine all this anisotropically, B1, also K2, and refine this one we can only refine isotropically, so the crystallite size distribution, and we can also increase the texture model to the 6th order just to see if we can improve the fit. And we do the same here for the apatite. B1 is already refined anisotropically by default, but we can do the same with K2 and refine K1, the size distribution, isotropically, and pump up the texture model to the next order, the 6th order. And now give this a try and see what we get. The fit looks really good now, and the chi-square parameter is now below 1.5. But let's still implement the refinement of the substitutions. but keep in mind that we need very good data quality for that. So here in this data set, we have very little peak overlap. The signals of appetite and calcite are well separated. If this was a worse quality than that, we would probably stop here and not refine atomic sites. But in this case, we can try. So in the calcite structure, we measured by chemical analysis some magnesium on the calcium site. So we wrap the scattering factors in parentheses. And we add site occupancies. And we parameterize them. So if we refine the content of magnesium with the parameter P, calcium is 1 minus P. And now we refine the parameter P. Starting at 0, no magnesium, keeping it in the positive range by setting the lower limit to 0 and the upper limit to 1 for full magnesium occupancy. And in the appetite structure, we will also implement a simple substitution model that places sodium on the calcium site, Na, and the parameter P is the sodium content on the first calcium site, starting at 0, keeping it positive, and limit at 1 for full sodium occupancy. And on the second side, we do the same. We can just copy this code here to the second line to refine sodium on this line as well. Now let's refine this and see what we get. And now we reach the chi-square value of 1.41, which was my best value, my lowest chi-square I could reach. Let's have a look at the list file showing the refined parameters. The quantities shown here, that's the same we see down here in the summary table. So we get 50.1 weight percent calcite and 49.9 weight percent hydroxyapatite, and you can probably guess that I created an artificial, a synthetic 50-50 mixture, and we are extremely close to the mixed values, to the mixed quantities. Let's look at the calcite structure, what we got here. We can see the calculated density and the refined A and C axis. The unit of these values is nanometers. And then we get some cryptic values for Gewicht, B1, K2, and so on. And down here, we can see the amount of magnesium that was refined on the calcium position. It was 5.63 atomic percent magnesium replaces calcium. Same for hydroxyapatite. You can see the calculated density, calculated from the structure data, A and C cell parameters, then the crystallite size in 2 different directions, some cryptic results for the K1, B1, K2, and Gewicht parameters. And then we found 7.47 atomic percent sodium on calcium 1 and 4.09 atomic percent sodium on calcium 2. And that is the best refinement I can come up with. And if I look at the scan, the refinement, especially the difference curve, it's always the best indicator to look at the difference curve. If there is any residual signal we have not fitted, that looks really good. So I would consider this refinement to be complete. The second exercise we want to process is example number 2. You will find 2 different scans. Again, always the new file format, BRML, and the old one. I will always use the new one, BRML. And these are 2 scans of reference samples of the LAB6, the NIST Standard Reference Material 660 version C, measured with 2 slightly different instrument configurations. You can see how the intensities change when I toggle between the two data sets. And the first data set was measured with my standard RMS D8 ADS instrument. So let's create a refinement project. Select the RMS D8 ADS instrument and search for LAB6. There's only one phase. We select it and we add it to create a refinement project. And then let's immediately run the first cycles, see what we get. And the fit is surprisingly poor for such a nice data set with so beautiful sharp peaks. And the first reason we can see in the structure file, the LAB6 structure file. In this file, the unit cell parameter A is not refined. This one is hard-coded to the certified value of this reference material. But obviously we need to refine it because it might not be exactly the certified value, for example, due to thermal expansion or contraction. So we start by just refining the A axis. Repeat it again. And that is already much better. Then we can check again if we should refine microstrain isotropically. We do refine some texture. So let's try with additional microstrain refinement. And then because we have such a wide data set going up to 120 degrees, we can try to refine some structural data. For example, the lanthanum ion is on a special position in the origin of the unit cell at X, Y, Z all 0. So we cannot refine them. The boron ion is also in a special position. Y and Z are 0.5, but the X coordinate is a general coordinate, so we can refine this one isotropically. And then we can also try to refine the thermal displacement parameter, which describes the vibration, the thermal vibration of this site. We only have it for the lanthanum position, but we can use the same code to also refine it for the boron position. I just copied this whole section here to the second line. And again, just to max out the refinement, we have such a beautiful high resolution data set. We can try to refine this stuff anisotropically. It probably will not make much of a difference. And now you can see that we get a fantastic fit with just some residual random noise at the positions of the peaks. Looking at the list file, we only have one phase, so obviously the quantity is 1. And then we can see the TDS, thermal displacement parameters, are very low. That's a good sign. So then they did not blow up. It's a stable solution. And also the X coordinate of the boron ion was just moved a tiny little bit from this starting value of 0.1991. It was moved to 0.20095, so just a tiny shift. That also looks like a stable solution to this fit. So this is a very good refinement for the first instrument configuration. Now, if we apply this, if we would use exactly the same refinement for the second file that was measured with a different instrument configuration, we can just copy this whole refinement project over to the other file. And we do that with this button here, copy the current control file to all open projects. If I click this, I can select my other project, or if there was a list of projects, I could select all of them and just apply my current refinement to these other projects. Now, if I go to the second one, I will have another control file that does exactly the same as we did in the first project. So we can just run the refinement. And now you can see that, especially at the lower angles, at 30 degrees and below, we have a massive problem with the intensities. And this is because I changed something to the instrument configuration. And as we can see on this slide here, the only difference is that I changed the divergence slit from an automatic setup that keeps the irradiated length at 15 millimeters to a fixed divergence angle of 0.3 degrees. So as we learned earlier yesterday, when we talked about finding the optimum instrument setup, the irradiated length changes with the fixed divergence slit as we scan towards higher angles. So we will get a different intensity evolution from the starting angle to the end angle. And this is exactly what we saw in the second data set, that the intensity evolution is different because I changed the mode of the divergence slit. So now, back in Profex, we want to implement this in the instrument configuration for the second data set. And first of all, we have to open the current fundamental parameters approach configuration of the second data set. And then we just go from the left, from the goniometer here, to the tube, and then down to the sample and up on the other side to the detector. Normally we would check every element here, the tube, divergence slits, Solar slits, but because I told you that I only changed the divergence slit mode, this is also the only thing we have to change here. So the divergence slit was no longer in variable mode, keeping the irradiated length at 15 millimeters, but it was in fixed mode with a beam divergence set to 0.3 degrees. That's the opening angle of the red lines here of the beam. That's an angle of 0.3 degrees. Now I don't want to overwrite my existing configuration because it's called after the divergence slit setting. ADS means automatic divergence slit. Here I used a fixed divergence slit, so I save it under a new name, but in my current directory, so I can immediately use it in my refinement project. So I save it, current directory, and then I call it RMS D8, which is a Bruker D8 advanced instrument, but instead of ADS, I call it FDS for fixed divergence slit. And then I give the value of the divergence slit, which is 0.3 degrees. So I call it 0P3. And then the detector links IXE.saf. So I save it under this name. I know it's a fixed divergence slit with a 0.3 degrees opening angle. Save. And now I can start the computation of the profile. I need to calculate the peak shape first. So I start the computation by clicking down here, Run Calculations, and it will take a while to create the peak profile. Okay, the calculation is complete. We don't need this editor anymore. Now, if we go to Locations, Current Project, we can now see that if I change this to Details, we can now see both the previous one, the RMS D8 ADS, and the new RMS D8 FDS configuration in this project folder. The first one will be used by our first project, And now we have to change our second project with the changed configuration to use this FDS configuration. And the way we do that is very simple. In the refinement control file, we have to change the Verzehr variable to use the other instrument, the FDS 0.3. Now if we run the refinement, it will be using the other configuration, and we will see if we get a better fit than before. And indeed, the fit is much better. This intensity mismatch is now resolved. We get a chi-square even below 1. And if we compare this to the first refinement, which had also a chi-square slightly below 1, it's now a comparable quality of fit for the fixed divergence slit setting. And this is the solution to these two exercises, how we improve the fit in the first one and how we create our custom instrument configuration file in the second exercise.